Everybody, in this video lesson, we're going to learn a new method for solving linear systems. It is called the method of elimination. So let's get started. I do have a bit of a warm-up / some motivation problems to help us to learn about this new method. I've given you a linear system, and they're both not in y equals mx plus b form. In our last lesson, we did learn a way to solve these. In this case, we could isolate the x and resolve for it. But in order to get my point across here, I'd like you to actually try to sketch these lines. So you'll need to rearrange both equations. So maybe I'll do the first one, and maybe you can pause and do the second one. So for the first guy, if we move the positive 1x over, we get 2y equals negative x, changes sign, plus 4. Now that's not y equals mx plus b. We'd like to divide everything by 2. And so we get y, and we have negative 1 over 2. X, 4 divided by 2 is 2. So that's great. There's our first line. Y-intercept of 2, down 1 over 2, down 1 over 2, down over 2, and so on and so forth. All right, so let's do our second line and see where they meet. So we've got to rearrange this guy. Maybe you can try it. It's a similar method. So if you want to pause the video and try it, or you can just follow along. So what if we rearrange that? We'll get 8y. And then the 4x goes over, so minus 4x, okay, and then plus 16. Then we want y by itself, so we'll divide everything by 8. Okay, so y equals, so we have negative 4 over 8. Well, in lowest terms, that's just negative 1 over 2. X, and 16 divided by 8, that's just 2. But if you guys look closely, we don't need to graph that line. We've already graphed that line. What we've just shown is that these two different looking equations actually represent the same line. Now, can you look at those two different equations? They are different. They have different numbers. They are different equations, but they represent the same line. How are they related to each other? So I might actually just put a pin in that question. Maybe you've got an answer to that problem. But let's look at one more. Can you maybe just try the same way here? Solve this linear system. Let's rearrange this first one. So we'll isolate the y bit. So 5y. We'll have negative 3x. And then we still have negative 10. And then we're going to divide everything by 5. Y equals negative 3 over 5x. Negative 10 divided by 5, that's exactly negative 2. So we can sketch this guy, no problem. Y-intercept of negative 2, down 3 over 5, down 3 over 5. And then back 5, up 3, back 5, up 3. So there it is. What if we do the same thing with the other equation? We're going to get minus 10y, and then that becomes positive 6 when you move it over, plus 20, okay? And then we'll divide everything by minus 10. So that's y, so 6 over minus 10, so that positive over negative, that is negative, and then 6 over 10 in lowest terms is 3 over 5. And 20 divided by negative 10, hey, that's negative 2 as well. These two equations, even though they look very different, actually represent the same line. And now we'll come back to the question we put a pin in. How are these two equations related? Can you see the connection between each of these linear systems? So looking back on the first one, if you said that equation 2 was actually just a multiple of equation 1, all the terms multiplied by 4, Great job. So equation 2 is basically 4 times equation 1. They're multiples of each other. And if you look at the second, the same thing happens here too. Equation 2 is actually equation 1 with all the terms multiplied by -2 times equation 1. All the terms multiplied by -2. The lines are multiples of each other. And hopefully what you're convinced of now is if you have one equation of a line and a second equation of a line that is just a multiple of that first one, they're going to be the same line, which is what our key idea here is, this idea of equivalent equations. So if you multiply an equation by a constant, we say that results in an equivalent equation because it produces the same graph. They are equivalent. And hopefully that these last two examples showed that. Now, actually, if we asked where do these two lines meet? Well, because they're actually the same line, they meet everywhere. Every single point on those lines is a point of intersection. So it's kind of a silly thing to ask since they're the same line. That's our big idea that's going to help us moving forward with this new method. Multiplying an equation by a constant results in an equivalent equation. It looks different, but it's the same line. So now that we've shown that, let's proceed and let's see how we can use that. So we're going to dive right in with this new method, elimination. So for today, I've outlined a clear structure with lots of scaffolding for you to use. And as we're going to see, I'm going to work through, and then eventually you're going to decide whether adding or subtracting the equations will eliminate a variable. So that was a lot up front. Let's walk through a couple examples and show you what I mean. So here we have a linear system. So 3x minus y equals 11 and 2x plus y equals 14. So it's not, the lines are not in y equals mx plus b form, but for this particular problem, you could rearrange them into y equals mx plus b form. And if you had a grid, you could graph them. It would not be impossible, but maybe impractical. You may also note for this one that it is possible to isolate the y in any of those equations. So you could use substitution for this one as well. But there's something special about this linear system that allows us to take a bit of a shortcut. So can you look at the linear system for a moment? Do you see what makes this one special? There's a bit of symmetry going on. You can pause the video and have a look and see what makes this special. Unpause when you're ready. All right, what makes this linear system a little different and a little special in a good way for us is that the y coefficients, it's the same coefficient, but they're just different signs. One is negative y, one is positive y. And I'll ask you, what happens when you add opposite numbers? What happens when you do, say, 3 plus -3? Or 6 plus -6, or 19 plus -19. What do you get? Hopefully you all said 0. So in linear systems where you have this nice matching up of the coefficients, we can eliminate a variable right away. In this case, because they're opposites, we can add the equations together. Because these guys have opposite signs. So it's a cool shortcut leading to this new method called elimination. So what happens when you add those? So those are opposite signs. Let's add those two equations together. So we're going to do 1. So again, we're doing addition. So what happens when you add equation 1 plus equation 2? So literally just add the x's, 3 plus 2, 5x. Again, when you add the y's, they're opposites. They're just going to give you 0. And then on the right, 11 plus 14, that's 25. Now, the equations we've been solving in our previous lessons, they by no means have been easy, but they were they've been relatively complicated, not too complicated, but we had to put in a bit of work. This equation here is easy to solve. 5x equals 25. 5 times what number is 25? Well, that just gives you x equals 5. And look how fast we were able to arrive at our value for x. So quick. And if we can recognize these situations where we have those matching coefficients, adding the equations can get you to a solution very quick. Now, our method for finding the other variable is the same as previous days. However, we'll have to do a tiny bit of extra work to get that other variable. So here's what I mean. Pick one of the equations to work with. It looks like they're both relatively easy to work with. So I'm going to sub into equation 2. So what happens when I do that? I get 2 times 5 plus y equals 14. So in the past, when we just used our calculator and it spit out the other variable, here we're gonna have to just do a little bit of solving, but it's not very difficult. In this case, we get 10 plus y equals 14, and then subtracting 10 from both sides, we get y equals 4. And we have our solution, 5, 4. So pretty cool. This is a new method. It's called elimination. And we can use elimination when the coefficients on, in this case, it was the y's, but we could have done it if it was on the x's too, match up. Let's look at another example. So here's a linear system. And if you look carefully, this one is kind of similar. If you look at this, guys, there's an interesting property of this linear system. The coefficients on the x's match up, but this time they're the same sign. So adding won't be very helpful, right? Because 2x plus 2x is 4x and nothing eliminated. But what happens if you subtract the same number, right? So for example, when you do 2 take away 2, or 10 take away 10, or even -5 take away -5. The answer to all these is 0. So if you have a linear system where the coefficients match and they're the same sign, you could subtract the equations to eliminate a variable. So watch what happens here. When we can do equation 1 minus equation 2. 3y subtract 1y is 2y. 5 subtract, and then equals. 5 subtract 3 is 2. And look at that. The x's are gone because they had the same sign. Subtracting them eliminated the variable. And dividing both sides by 2, we just get that y is equal to 1. Our y value is 1. That's great. And then we can find x the same way we've been doing. We sub into an equation. To me, it looks like they're both the same level of difficulty. So I'll just pick equation 2 just because. So 2, we want to find out what x is, plus 1 equals 3. Bring the 1 over, just subtract it from each side. We get 3 minus 1 is 2. And 2 divided by 2 is 1. X is equal to 1. Hey guys, that's great. We found our solution to this linear system. It's 1, 1. So we now have had 2 examples of a new method. This method is called elimination. And you can use it when your linear system has matching coefficients that are opposite signs, in which case adding the equations eliminates a variable, or if you have coefficients that are the same number and the same sign, subtracting them will eliminate a variable. And in practice, it's going to be up to you to recognize when you can use elimination and to recognize if you're going to add or subtract, if either one of those will help you. But hopefully you're convinced when this happens, when you add or subtract, you are left with something very easy to solve. And then plugging it back in takes a little bit more work, but arguably not very challenging at all. This method can be really good. It can save you a lot of time. But as I've just been mentioning, it only works when you have these, matching coefficients, which isn't going to be true all the time. Or can it be true all the time? Consider this example. So here we have 3x plus 4y equals 11, 2x plus y equals 4. So what happens if you add the equations? What happens if you subtract them? Can this just work all the time? If you add the equations, so you get 3x plus 2x is 5x. 4x plus y, or 4y plus y is 5y. And 11 plus 4 is 15. And if you subtract the equations, so 1 subtract 2, you get 3 minus 2, that's 1x. 4 minus 1y is 3y. 11 minus 4 is 7. And we haven't really gotten anywhere. None of the variables were eliminated. I can't solve any of these equations because they all have 2 variables in them. So in general, you can't just add or subtract equations and for things to work out. And to use elimination, to add equations, subtract, you need to have matching coefficients. Same center, opposite sign, but the same number. So what can we do? We need to, lots of people in the building doing maintenance and stuff like that. As I said earlier, we plow on. No editing team to come in and edit that out later. So we're going to need to modify our method to help in these sorts of cases, because we would like some way to change the equations to make the variables match. Because again, if they don't match, adding, subtracting doesn't help. They have to match. Well, how can we make them match? Think back to the motivating problems I had you guys do. Remember, when you multiply an equation by a number, it doesn't change the equation. It's the same equation, looks different, but it's the same equation. So what we can do is we can multiply an equation by a constant and get an equivalent linear system that maybe we could solve using elimination. So let's see what I mean by that. Excuse me. So here's that linear system we just looked at. So adding or subtracting blindly won't work right now, but can we make the x's or y's match up with a simple multiplication? So can you see which equation can we easily multiply and match up variables? So think, are we going to match the y's or the x's? And which equation should I multiply and by what number? So if you want to pause and think about that, unpause when you're ready. But here we go. So if you said that you could take equation 2 and multiply it by 4, good for you. Because check this out. So we're not going to touch the first equation. We're going to leave that alone. But multiply everything in equation 2 by 4. We get 8x, 4y, and 16. And remember, everything, right and left side, multiply by 4. Now look, those variables match up. So we could subtract these equations and easily eliminate a variable. And we are subtracting because it's positive and positive. We want them to cancel out. Now, whether you subtract equation 1 minus equation 2 or equation 2 minus equation 1, it doesn't matter. To mix things up, I'm going to subtract equation 2 minus equation 1. It just so happens that this also just helps us avoid negatives in this question, which is generally a good thing. Keep things as simple as possible. But look, guys, 8 take away 3, 5x. 4 take away 4, 0y. 16 take away 11 is 5. And look at that simple equation we're left with. 5 times 1 is 5. X equals 1. Pick an equation to work with, and we're going to pick one of the originals. And I think equation 2 looks easiest to work with here. I think I've been choosing 2 a lot, but I can assure you it's just coincidence. I just always pick the equation that works the easiest for me. So 2 times 1 plus y equals 4. 2 plus y equals 4. Hey, I know that 2 plus 2 is equal to 4. So y is equal to 2. And we've solved this linear system. The solution is the point 1, 2. That's the point of intersection between these 2 lines. And I would argue that This method is pretty slick. Nothing in here overly complicated. What you do have to recognize is you have to be able to look at your linear system and think, how can I match up some variables here? And in this case, it was very easy for us to multiply this y by 4, do the whole equation by 4, match up the y's, and so we can use elimination here. So really cool. Can you try this one? Maybe on your own. Pause and unpause if you're stuck or when you want to check your solution. But look at the linear system. Think how we can match up some variables. So I'm going to keep going now. If you recognize that you could take equation 1 and multiply it by 4 to match up the x's, good for you. The new linear system would be 4x plus 12y equals 36, everything by 4. Remember, some people forget that you have to multiply the right-hand side by 4 as well, so please don't let that be you. And we're not touching the second equation because it had the 4x that we wanted. Alrighty, so do we add or subtract? Well, we have the same sign. It's 4 take away 4. That would give us 0. And I'm going to do equation 1 minus equation 2 here. And you can do either order, just got to be careful. Especially with negatives, these examples so far have had mostly positive results. But you could get into a scenario where you have to do -3 take away -5 or something. And we've all have lots of experience working with integers. So that would be like -3 plus 5 or 2, but you just have to be careful. All right, so let's do the subtraction. So 12y minus 5y is 7y. 36 minus 22 is 14. That works out good because you divide by 7, you get that y is equal to 2. So now the y value is 2. And I think equation 1 looks easy to work with here. So x plus 3 times 2 equals 9. X plus 6 equals 9. And it's 3 plus 6 that equals 9. So x equals 3. Our solution, 3, 2. If we were to graph those lines, they would intersect at the point 3, 2. That's great. So I think this is, this one more example for you guys to try. And I would really encourage you to, pause the video or like rewatch the previous 2 examples and try this one purely on your own. It's great to follow along and copy the examples down, but again, especially with the way that school is happening right now and the way we're kind of running classes, we need to, for better or for worse, you guys have to develop that resiliency and independence a little bit faster than you may have in other years. So really try it on your own. If it doesn't work out, that's okay. Just unpause the video and follow along. All right, so if you suggested to match the y's by multiplying equation 2 by 3, good for you. The new linear system would look like this. 3x plus 3y equals 9, equation 1. And then we would get 15x minus 3y, and 3 times 9 equals 27. And in this case, we've matched the y's, but because they're opposite signs, adding will eliminate a variable here. And we get 18x. Again, we're adding, we're doing 1 plus 2. 18x, the y's go away, and 9 plus 27 is 36. This works out nice because 36 divided by 18 is exactly 2. So x is 2. And which equation looks easier to work with? It doesn't really look like one's better than the other. I'll choose 1. So 3 times 2 plus 3y equals 9. 6 plus 3y equals 9. So let's bring the 6 to the right. By subtracting it off, we get 3y. 9 minus 6 is 3. And dividing by 3, we just get y is equal to 1. All right, guys. So we've done several examples now with this new method. And this method is awesome if you can make the variables match up. And in our very first examples, sometimes the linear system you have, the equations, the coefficients match up right away, and you can add or subtract right away. Sometimes they don't, but you can make them match by doing a clever multiplication. And so what you guys need to work on is being able to identify, am I adding or subtracting to a limited variable? If my coefficients don't match, can I find a way to make them match by multiplying one of the equations? And what you'll also have to do is, because this is a brand new topic, I've given you a lot of structure here. What you guys need to be able to do is, if I just say gave you this linear system and that's all you got, you need to be able to apply this method. I've given you a suggestion for how to structure that solution, but we need to be able to move towards, you not relying on me for structure. You know the steps and you can carry them out. So that's where practice comes in. So yeah, definitely practice, reach out if you need some help. What we're going to be doing next is we're going to look at examples where multiplying a single equation won't exactly cut it. So for example, pretty easy to make up one like that. So I'm just making up a linear system on the fly here. 5x plus 7y equals 9. So looking at this linear system, one, graphing, I don't want to do that. Two, could I use substitution? Is there an easy way to isolate a variable? And the answer is no, there's not. They're all the variables being multiplied by a number. And thirdly, could I use this new method of elimination, adding or subtracting equations with matching coefficients? So right now, nothing matches. Is there an easy way to make things match? Well, no, there's really no nice whole number to multiply 3 by to get 5 or 4 by to get 7. So what can we do in this cases? We can do something. I'm going to show you guys that next lesson. We'll also try to work on removing some of the structure and being able just to solve these on our own. But that's it for now, guys. Until I see you guys again, hope you're doing well. Have a great day, and we'll see you soon.